Hello, I'm John Dwyer, author of Multifactorials and Primes for Cryptography. This time we're looking at types of prime numbers, which are covered in chapter 3 of the book, and we'll look at the slides now. So we're looking at chapter 3, different types of prime numbers, particularly those that are applied to cryptography. And the first type of prime number that we'll look at is the Cuban prime. Now, generalized Cuban numbers, nothing to do with Cuba, are in fact defined as the difference between two cubes. In its general form, Cuban Mn, where M and N are both positive integer, is n cubed minus n minus m cubed. You can see that the expression simplifies, and in the particular case where m equals 1, Cuban n, which is a function of one variable, is equal to n cubed minus n minus 1 cubed. And that's the function and definition that often appears in textbooks. Turns out that the Cuban numbers which are prime are 7, 19, 37, 61, and so on. And it's a particular type of formula-based prime number. The next one is Proth prime. A Proth number, named after Francois Proth, a French mathematician, is a number in the form k 2 to the n plus 1, where k is odd and 2 to the n is greater than k. We need this condition because otherwise virtually every number would be a Proth number. A Proth prime, which is a Proth number that happens to be prime, the list is 3, 5, 13, 17, 41, and so on. Very important for at least two reasons. One, a special case when k equals n in a Proth number gives a Cullen number, which is described also in chapter 3. A Fermat prime, which is the special case k equals 1, is also a special case. Now, it turns out Proth primes can be tested really quite easily compared to other numbers of similar magnitude. And of course, in cryptography, we're looking at numbers with 100, 150 decimal digits, large numbers. Anyway, the Proth prime type is formula-based. Ramanujan primes are primes which are counted as being in part of an interval. So if we consider an x and an x over 2, where x is a large increasing number, we count how many primes are in that particular interval. And that gives us a Ramanujan prime. 2, 11, 17, 29, 41. And these are named after Srinivasa Ramanujan, famous Indian mathematician. Property-based. Regular primes are primes which happen to divide the numerators of the Bernoulli numbers. Now, it's not important how to derive the Bernoulli numbers. They are important in number theory, differential equations, and so on. But we know the numerators are 1, 5, 7, 6, 9, 1, and so on. And it turns out that the regular primes are 3, 5, 7, 11, 13, 17, etc. A prime number which is not regular is called an irregular prime. Makes sense? So the prime type for regular and irregular primes is property-based. Now, Solinas primes, named after Jerome Solinas, an American mathematician, is a function of two variables, m and n. Again, m and n are positive integer, in the form 2 to the m plus or minus 2 to the n plus or minus 1. So you can see there are four possibilities depending on the pairing of plus and minus. And the first few Solinas primes are 3, 5, 7, 11, 13, 17, 19, and so on. Numbers which are not primes, not Solinas primes, include 43, 53, and so on. Now, the Solinas primes are special cases of Mersenne and Crendel primes, which are both discussed in chapter 3. A striking property of Solinas primes, well, there are several, but one is that when you take a decimal Solinas prime and convert it to base 2 binary, you get three digits which are 1. No matter how big it is, there are only 3 ones in the binary form of a Solinas prime. Solinas prime is formula based. Now, the definition of a Sophie-Germain prime is really quite simple, 2p plus 1. And they are 2, 3, 5, 11, 23, and so on. But in 1825, she proved that Fermat's last theorem is true for odd Germain primes. Turns out in chapter 7, we prove Fermat's last theorem for all integers, not just those which are odd Germain primes. Sophie-Germain primes are property-based. Supersingular primes are prime numbers that relate to elliptic curves and modular functions. There are only 15 of these, 2, 3, 5, all the way up to 59, 71. Turns out they are a set or a subset of the Chen primes. Non-supersingular primes are 37, 43, etc. Supersingular primes are property-based. Now, unique primes are a digit-based prime number. So we look at a third, 0.3 recurring. We look at 1 over 11, 0.09, 09, 09, etc. We can see for certain fractions or reciprocals that you have a cycle going on. And those cycles define the unique primes. 3, 11, 37, 101, 9091, and so on. Unique prime type, digit-based. Now, Wagstaff, an American mathematician, defined a prime number to be of the form 2 to the q plus 1 over 3, where q is an odd prime. The first few Wagstaff primes are 3, 11, 43, 683, and so on. In particular, for Wagstaff primes, the cryptographic algorithm ECPP, elliptic curve primality proving algorithm, is one of the fastest known algorithms for taking a Wagstaff number and proving if it's a prime. We'll look at this more in chapter 6 of the book. Wagstaff prime, formula based. Now in the book we look at 100 of the order of 100 different types of prime number, and we try and classify them. Constellation based, Sophie-Germain, twin, sexy, and so on. Digit based, additive, happy, minimal, Padovan. Factorial based, Euclid number, factorial, fortunate, etc. Now formula based, we've seen a few of those today: Cuban, Fermat, Mersenne, Wagstaff. Property based, Ramanujan, good, fortunate, and so on. Recursion based, well, most of us know the recursive definition of Fibonacci numbers. See them in school: factorial numbers, Pell, primorial. And then finally, size based, no surprise that in cryptography we're looking at very large numbers, particularly prime numbers. And in that case, we look at gigantic, largest known, mega, titanic, and so on. So, if you have any questions or any comments to make, email me at the university, john.dwyer@roehampton.ac.uk, and thanks for listening. Bye.